So we've collected an IID sample, and we'd like to learn something about the probability distribution that's making the data. So maybe we know what the distribution is, we just don't know what flavor it is, like it's a Weibull, but we don't know its two parameters. And so we might like to come up with a best guess for what those parameters are, a good guess for how far off our estimate is from the truth, and then also a range of plausible values for those parameters that are consistent with the data that we've collected. Or maybe we don't know what probability distribution is making our data. We don't really care. We just want to estimate the mu parameter of that distribution, the expected value or the average value of that probability distribution. And we have some pretty easy to use formulas that allow us to come up with the best guess and also a confidence interval just by taking that best guess and then moving about 2 standard errors away. And with R, it's fairly easy to get out these confidence intervals just with the fitDist command or with the t.test command. Now, why did these formulas work? Well, it was because the sampling distribution of our guesses had a known distribution. It was approximately normal. And so what that meant was realizing that when we go and collect data, the values that we collect are random, and therefore our best guess, the MLE, or the sample average, is going to vary from sample to sample depending on what data values we happen to collect. But if we envisioned all possible samples that could ever be generated and looked to see what the distribution of the MLEs or the sample averages are on those samples, we saw time and time again that it had a predictable shape. It looked approximately normal. And there was a special spot on that normal distribution that allowed us to quantify typically how far off values were away from the peak. So we called this value the standard deviation. We had to guess what that standard deviation was, the distance between the peak and that inflection point. So we called it the standard error. But there was some math, there was some analysis that allowed us to come up with values for these quantities. And so we could very quickly just run t.test or fitDist, or just by hand come up with these confidence intervals. And the great thing about estimating mu, the expected value of our probability distribution, is that we really didn't need to know what that distribution was. As long as we were dealing with a large enough sample, the sampling distribution of that sample average, the distribution of the possible sample averages we might observe when we go and collect data, looked like this normal distribution with a peak and a standard deviation that was predictable based on the mu and sigma parameters of the probability distribution that was making our data. Now, we did have one caveat when coming up with a confidence interval for theta or for mu, and that caveat was that we had to have enough data for this procedure to go off without a hitch. When coming up with a confidence interval for the theta parameter of a probability distribution, we needed at least about 24 or so data points. If we were making a confidence interval for the mu parameter, the average parameter of that probability distribution, well, that was tied into the shape of the histogram of the data values that we made. As long as we had at least 100 data values, we knew we were good to go. We could get away with fewer data points if the histogram looked roughly symmetric. And so what's going to happen, though, if we find ourselves in a world where we don't have enough data? So maybe we don't have enough data points for that central limit theorem to be in effect and to use t.test to come up with a confidence interval for the average. Maybe we don't have enough data so that the asymptotic normality of the sampling distribution of the MLE doesn't really quite apply. What are we going to do in those situations? Or it might just be the case that there's a parameter of that distribution, like the interquartile range, the difference between the 75th and the 25th percentiles, that we don't really have the theory for to guide us into coming up with a good guess or a confidence interval for those values. So what if there was another way to actually come up with a glimpse of what the sampling distribution is of some statistic that we have in mind that didn't rely on really fleshing out all of the complicated theory behind it? And there is, and the procedure is known as the bootstrap. The bootstrap's going to allow us to glimpse the sampling distribution of a statistic that we have in mind, how that value of the statistic might unfold if the data values came out a little bit differently. And we're going to be able to use those glimpses to come up with a range of plausible values for the parameter we're trying to estimate just from the one set of sample values that we've collected. So let's motivate this. Let's see how this works with the following scenario. So let's imagine that we've collected the following set of 6 data values. We've collected a 1, 3, 5, 2 9s, and a 12. So we could measure a single value of x bar. If we knew this data was coming from Poisson distribution, we could come up with an MLE estimate. But we would like to know how far off our estimated value is from the true value of the parameter of the probability distribution that's making the data. So to make that statement, we need to know something about the sampling distribution. We need to know how far off x bar, or how far off the MLE, might be away from the true value of that parameter we're trying to estimate. So we need to know something about the sampling distribution of that statistic. What are the possible values we might observe? What are the respective frequencies when we go and collect data? Now, with one sample, you might think that our hands would be tied behind our back. But what if we did the following? What if we just put all the collected data values down into a bag, reached down into that bag, and drew one out at random, placing it back before drawing another data value, and we kept doing this until we generated a sample of the same size as what we started with. So what if we went and measured the value of the statistics on those alternative samples? So maybe the first alternative sample that I come up with has the numbers 5, 1, 12, 5, 3, 1. Maybe another alternative sample just has all 5s, just kind of by weird luck. What if we looked at the values of the statistic on each one of those alternative samples and used that as our glimpse as to what the sampling distribution of our statistic really is? Well, let's go with this. Let's actually go and generate a whole bunch of alternative samples, each just sampling with replacement from the original data values that we've collected. And in this case, let's go ahead and just look at the sample averages of those alternative samples. Let's make a histogram of those to see what the sampling distribution of the sample average looks like as we go from one alternative sample to the next. And so when I make a histogram of the averages from all those alternative samples, I see a pretty familiar shape. In fact, the shape of this looks more or less like a normal curve. I can draw a blue line to represent where that inflection point is of that normal curve. And this gives me an idea of how variable my sample average might be when I go and collect data. Now, I only have that one sample, but I can glimpse at how variable that value of x bar might be from other sample to other sample by just looking to see its distribution across these alternative samples. So if I use that distance from the peak of this normal distribution, or normal looking distribution, to that inflection point and just call that my standard error, my best guess for how far off x bar might be from mu, well, maybe I'm onto something. So let's run with that. Why don't we use as our standard error of our estimated value, our x bar from our original sample, just the standard deviation of this inferred sampling distribution across all these alternative samples. And why don't we just go ahead and use as our 95% confidence interval the range of values between the 2.5th and the 97.5th percentiles of this inferred sampling distribution. Now, in between those two percentiles, we have 99 or 95% of the values, and so that seems like a reasonable thing to do. I mean, that's what we were doing when we were assuming that the sampling distribution of the MLE, or the sample average, had a normal distribution. 95% of the values of a normal distribution are within plus or minus 2 standard deviations within the 2.5, 97.5th percentiles, and so the procedure is roughly analogous. So for this example, if we go and ask, well, what's the 2.5th and the 97.5th percentiles of these alternative samples, x bars here, I get a confidence interval that ranges between 3.3 and about 9.5. How would that compare to the confidence interval that came out from t.test? Well, there's a little bit of a difference here. I'm only dealing with 6 data values, so probably neither of these two procedures are all that reliable, but the answers are matching up close enough that maybe I'm onto something. And so let's run with this. This is actually something people explored back in the day, and they found that it worked actually pretty well. We're going to call this procedure the bootstrap because we're essentially lifting ourselves up by our own bootstraps, kind of glimpsing to see what the sampling distribution of that sample average, or the MLE, is, if our data might have turned out a little bit differently just by generating these bootstrap samples, just by sampling with replacement from the data values that we have. If we look at the standard deviation of those Bootstrap estimates, well, we can treat that as the standard error of our originally estimated statistic. And if we use the percentiles of that inferred sampling distribution, we could call that the Bootstrap confidence interval. And the great thing about this procedure is that there's really no requirements to really use this. There's no sample size requirement. We don't need to know what the probability distribution is that's making our data. We can just take our one sample of collected data values and just run with it. If there's something we want to estimate about that probability distribution, well, find a way to estimate it from a sample, look to see how the sample values might have turned out a little bit differently. Use that as the approximate sampling distribution of our statistic and create a confidence interval from there. So as a proof of concept, let's just see how this Bootstrap procedure works when, say, estimating the MLE of a Poisson distribution, that lambda parameter. So in this case, the lambda hat, the MLE, is just the sample average, so it's like estimating the mu parameter as well. Let's go ahead and generate a random sample from the Poisson distribution where we know what the value of lambda is, so we can check our confidence interval to see if it got it right. Let's take lambda equal to 3. And let's go and create 499 Bootstrap samples, just by sampling with replacement from my originally collected data values. In this case, what I find is that the MLE on the original data values is just 2.33. If I'd like to know, well, how far off is that guess? Probably away from the true value of lambda here. I can look at the standard deviation of my Bootstrap estimates. So I'd take my standard error to be about 0.345. And if I looked at the 2.5th and the 97.5th percentiles of that inferred sampling distribution, how variable those X bars were from alternative sample to alternative sample, I would say that I'm 95% confident that the true value of lambda is somewhere between 1.67 and 3 here. So does this procedure work? Whenever I develop a confidence interval, it's some sort of procedure that by design, the range of values that come out from it should have a 95% chance of covering the true value of that parameter that I'm trying to estimate. So what's the achieved level of confidence of this Bootstrap procedure? How often when I implement this Bootstrap procedure do I come up with a 95% confidence interval that contains the true value of the parameter I'm trying to estimate? Well, I can go and run this experiment a whole bunch of different times. Maybe in each of 10,000 different trials, I generate a new Poisson random sample just with the rpois command, taking 15 values with a lambda equal to 3. So each one of these 10,000 trials, I'm dealing with a slightly different random sample of values. And then for each of those random samples, go and create the Bootstrap confidence interval. Check to see if 3 is inside that 95% confidence interval. And then after my simulation is concluded, I can ask, well, what fraction of those 10,000 different random samples did my Bootstrap procedure end up with a range of values that contain 3? And when I do this, I find that I get about 90%. So well, that's a little disappointing. I designed my procedure to have 95% confidence. The achieved level of confidence is more like 90%. But I'm in the ballpark. I didn't really have to do any math. There was no theory that really guided this. Lifting myself up from my own bootstraps here, kind of glimpsing to see how variable my statistic, my estimator might be if the data values turned out a little bit differently. So that's actually really cool that I'm ending up that close to getting an achieved level of confidence as close as to the designed 95% level. Now we might be curious to see, well, what's the achieved level of confidence using our MLE procedure or using the t-dot test procedure. So we have some really good theory that allows us to construct approximate 95% confidence intervals. So what's their achieved level of confidence? So with the MLE, it turns out that an approximate 95% confidence interval for the Poisson's lambda parameter is just x bar plus or minus 2 times the square root of x bar over n. Using t-test, since mu is the same value as lambda in this case, we find actually after a similar simulation that the achieved level of confidences of both these procedures is really quite close to 95%. So not too surprising when we inject a lot of theory into this, a lot of stuff that's very well known, we achieve a level of confidence much closer to what we designed. But there was a lot of math and a lot of work that went into coming up with how to get those confidence intervals. The Bootstrap, we just use our original data set of data values and we just go from there. And so this has become a more and more common way of estimating parameters of probability distributions. We're going to call this the percentile bootstrap method because from our single set of collected data values, we're going to infer what the sampling distribution is of the statistic that we've chosen to measure to estimate that unknown parameter of the probability distribution. And we're going to use the percentiles of the inferred sampling distribution. 95% confidence interval, we use the difference between the 2.5th and the 97.5th percentiles of that inferred sampling distribution. 90% confidence interval, well, that would be the range of values between the 5th and the 95th percentile, so that 90% of the values are between those two. So let's illustrate how this works just with a few examples. So back in the day, we recorded the fastest speed that IntroStat students had ever driven. So we'll assume that this is a random sample from some probability distribution. We don't know what it is. We want to estimate the mu parameter of that probability distribution. And with so much data in this case, over 600 observations, t-test is going to work like a charm. The central limit theorem is going to be in full effect, regardless of what the shape of the histogram ends up looking like. But let's see how the bootstrap works. So we'll create 499 bootstrap samples, just sampling with replacement from the originally collected data values until we have a sample that's the same size as our original. Once we've made those bootstrap samples, we can ask for the 5th and the 95th percentiles in order to get a 90% confidence interval. And we find that based on our bootstrap work, 90% confident that mu is between 101.2 and 103.5. How does that compare with the t-test confidence interval? Well, it's really quite close. There's really hardly any difference whatsoever. We're able to come up with a range of plausible values for that mu parameter without having to rely on really theory at all. What if we wanted to estimate, say, the percentile of some probability distribution without knowing what that probability distribution is? So here we have a collection of customer lifetime values, and we might be interested in making a 95% confidence interval for the 80th percentile of whatever probability distribution is making this data. So I could estimate that 80th percentile just from the 80th percentile of my collected data values. So my best guess might be about $2,030. But what's a confidence interval for that? What's my standard error? How far off do I think that value might be from the truth? And what's a range of plausible values for the 80th percentile of this distribution? Well, what I can do is I can go and create 499 bootstrap samples to figure this out. So for each one of those 499 bootstrap samples, I'll just create a sample of equal size just by picking with replacement from my originally collected data values, and I'll ask for the 80th percentiles of each one of those. So once that's done, I could get the standard deviation of those bootstrap estimates to come up with a standard error of my original guess, the 80th percentile from the data values that I've collected. And I could use the percentiles of the bootstrap estimates to come up with the confidence interval. So looking at the 2.5th and the 97.5th percentiles, it's going to give me a 95% confidence interval. And so I could say I'm 95% confident that the 80th percentile of this probability distribution is between 1881 and 2192. So how does that compare with the exact confidence interval that the getCI for percentile function gives us? Well, asking for that confidence interval, we find that the confidence interval for the 80th percentile are just the values between the 383rd smallest value up to the 418th smallest value. And we get a very similar looking confidence interval ranging from 1898 up to about 2204. So without having to know anything about that probability distribution, without having to know really anything about theory whatsoever, we've come up with a pretty reasonable range of plausible values for what that 80th percentile is just by lifting ourselves up by our own bootstraps, creating these bootstrap samples. What if we wanted to look at the difference in averages, say between the probability distributions that's making data between two different groups, the difference in those mu parameters? Well, our strategy is going to be very similar. We're going to create bootstrap samples just for each sample in and of itself. So if I wanted to compare, let's say the average lifetime value of men and women for this store, I can create bootstrap samples for men, bootstrap samples for women, and see how the difference in averages compares across my collection of bootstrap samples. If I do this, making bootstrap sample for men and bootstrap sample for women at each iteration, I can look back and say, okay, well, what's the 2.5th and 97.5th percentiles of the differences in averages from one set of Bootstrap samples to another set? And I would come up with a confidence interval that ranges from minus 14.8 up to about 280. Zero's inside that confidence interval, so I don't see a statistically significant difference in the average lifetime values. And I would find I'd get a very similar result if I just ran t-test. So the 95% confidence interval that relies on the central limit theorem being in play, and in this case we have a large enough sample if that's the case, we get a very similar looking confidence interval and the same conclusion. So we can even use the Bootstrap procedure to get standard errors and confidence intervals for, say, regression coefficients. So we can imagine that there's probably some sort of relationship between the number of wins that an NFL team makes over the course of their 16 games per season and the number of fumbles they make while on offense. Looking at the collected data, we find that there's a slightly negative relationship. The trajectory of that stream of points is roughly linear, so a linear regression might do a good job at describing this relationship. So if I compare two teams that differ in the number of fumbles they make by one, how do I expect the number of wins to differ over the course of the season? Well, that's a question about the regression coefficient when I try to predict the wins from the number of fumbles. So can I come up with a 95% confidence interval for this difference, a 95% confidence interval for the regression coefficient? Well, the answer is going to be yes. The way that I'm going to do this, because I have two values I'm really studying and the relationship between two different values, when I go and create a Bootstrap sample, I'm going to actually sample rows from my data frame. And so that way the relationship between wins and fumbles kind of remains intact. I'm just bootstrapping pairs of values instead of individual values themselves. So if I make enough Bootstrap samples, measure the regression coefficients on each one of those, I can go and ask, well, what's the 2.5th and 97.5th percentiles to come up with a 95% confidence interval for this regression coefficient. And so in this case, my 95% confidence interval goes from minus 0.23 all the way up to minus 0.15, and that kind of makes sense. So two teams that differ in the number of fumbles they made over the course of the season are expected to differ in the average number of wins by about minus 0.5 down to minus 0.23, with the team with the larger number of fumbles having the lower average number of wins. So using the Bootstrap to make inferences on a probability distribution, really not so bad. What's our best guess of some parameter, theta, of a probability distribution? Well, whatever the best guess is from the sample values, maybe the average or the MLE estimate. What's our idea of the standard error? How far off might that estimate be from the true value of the parameter? Well, we can look at the standard deviation of the Bootstrap estimates over our Bootstrap samples. What's a 95% confidence interval for that parameter we're trying to estimate? Well, just the range of values between the 2.5th and the 97.5th percentiles of those Bootstrap estimates. Now, this percentile bootstrap method is amazing. We hardly need to know anything about the probability distribution that's making the data. We don't really need to know much about statistical theory. We just kind of get those standard errors. We get those confidence intervals out of nowhere. But there are some drawbacks. There are some shortcomings to this percentile method that we'd like to correct for. So number one, it might turn out that our Bootstrap estimates are biased. We've talked about biased estimators before. On average, maybe the estimated value comes in a little bit too high, above the true value of the parameter, or maybe sometimes a little bit too low, below the true value of the parameter. We saw that when trying to estimate the upper bound of a uniform distribution that ranged between 0 and theta. If we use the MLE estimate, our MLE estimate systematically always came back with a number that was a little bit too low. But we had a way to actually correct for it. If we could anticipate what that bias was, we could correct for the bias of our estimator and come up with an unbiased estimate. Now, it turns out that the percentile method very often ends up with an estimator in a Bootstrap confidence interval that's a little bit biased. We find that the achieved level of confidence isn't quite equal to the target level of confidence of 95%, and people have figured out a way to correct for this. And so instead of using the percentile method, which is very easy for us to code just on our own, there's another way of pulling off the Bootstrap called the BCA method, or the bias corrected and accelerated method. That is the preferred way to do this. and that'll correct for the bias in the original procedure and kind of converge to a better set of estimates a little bit faster. That's what the accelerated part deals with. So how do we do this? Well, the math behind it is a bit beyond the scope of this course, but the nice thing is that there's a package in R called Boot that will come up with these BCA Bootstrap confidence intervals for you. You just have to set it up correctly. So how are we going to get these BCA confidence intervals? Well, we're going to run the boot command. The first argument of boot is going to be the set of originally collected data values, the data argument. The second argument is going to be estimator equals. And here's where we're going to write a function that tells the boot command what to measure from each one of the Bootstrap samples it's going to be creating. So like the average, the 80th percentile, etc. The third argument, R, talks about the number of Bootstrap replications. 499 or more is typically good, but we have some control over that. So let's talk about this estimator function. The estimator function is letting the boot command know what to measure from each one of those Bootstrap samples, the average, the 80th percentile, the MLE, estimate of some probability distribution, etc. And there's some very special syntax that we have to respect with this. So when we write our estimator function, our first argument is always going to be x, just referring to the vector of data values in the Bootstrap sample. And the second argument is always going to be indices. And whenever we write our function that tells estimator what to measure, we're always going to refer as x bracket indices to the values that are being used in the estimate. Why is this the case? Well, indices is basically a little placeholder for what positions inside the original data vector we ended up selecting these Bootstrap samples from, and it's just a quirk that we have to respect. So if I'm going to be measuring the average value of each one of those Bootstrap samples, inside that estimator function, I'm just going to write mean of x bracket indices. If I'm going to get the median, it would be the median of x bracket indices. Percentile, you get the idea. So quantile, x bracket indices, comma 0.8, say for the 80th percentile. Or for the MLE, I could actually use fitdist inside that estimator function. I would say fitdist x bracket indices, give it the name of the probability distribution I'm using, and then slap the $ estimate at the end to just extract out the MLE estimate. So once that command is completed, I'm one step away from getting my BCA confidence intervals. I'll run the command boot.ci on that object that was created by boot, and I'll say type equals BCA. I could do type equals PERC to get the percentile method as well. I could compare those two, and I'll put in a level of confidence that I want the confidence interval to have. So a quick example of coming up with a BCA Bootstrap confidence interval for the mu parameter of a probability distribution. Let's imagine that we have a vector of 50 data values. In this case, I'm generating them from a log normal distribution with both parameters equal to 1. To do the BCA Bootstrap confidence interval, I need to define that function estimator. So estimator left arrow function, first argument x, second argument indices, and then inside the curly bracket, I need to write out what I'm going to be measuring for each of those Bootstrap samples. So what I'm going to do is simply put x bracket indices and then surround that with the mean function, since that's what I'm going to be estimating from each sample. Once I've defined the estimator function, all I need to do is run boot. So first argument is my vector of data values, second argument is estimator, and then the number of Bootstrap samples that I want to create, 5,000 in this case. Once that object has been created, calling it b.mean here, I'll run boot.ci on b.mean, type equals BCA, and for fun, let's do a 90% confidence interval. We run it and we find that we're 90% confident that the true value of mu for this probability distribution is somewhere between 5.3 and 8.4. So for example, if I wanted to come up with BCA confidence intervals for regression coefficients, well, when I set up my estimator function, that first argument is going to be x, the data values in the Bootstrap sample that I'm going to be using to come up with my estimate. The second argument always going to be indices. And in this case, what I would set it up as predicting wins from the number of fumbles. And the data argument for LM, my linear regression command, would just be x bracket indices here, because I'm going to be sampling rows of the originally collected data frame here, and then slapping a $ and adding coef to get the coefficients of that Bootstrap sample here. And in this case, since there's two values that come out, the intercept and the slope, I could ask for index equal to 2 because it's the second of those two values. The intercept is always first. And that would allow me to come up with a BCA confidence interval for the slope of this regression line, the regression coefficient. So you might be wondering, this BCA method, Bootstrap in general, is a pretty cool method for coming up with confidence intervals. Can we always just bootstrap? And the answer almost always is, yeah, you kind of can. There are some weird statistics for some parameters that don't really lend itself well to the bootstrapping technique, but those are ones that you would hardly really ever run into. I think the classic one is that if you're trying to come up with, say, the upper bound of a uniform distribution, the bootstrap sample is never really going to help you out in that case. You really need to rely on statistical theory. That's where calculus broke down. That's where fit disk broke down as well. So for those cases, bootstrap's not going to help all that much. But for the most part, yeah, you can come up with confidence intervals using this bootstrap method for almost any parameter of a probability distribution you're curious in studying. How many bootstrap samples do you really need? Well, the guideline is as long as you're making roughly 500, 499 bootstrap samples or more, you're going to be good to go. That procedure is going to be fairly reliable. The more bootstrap samples, the better. It just takes a bit more time. The important thing, though, is that once you have done that bootstrapping, is actually looking at the distribution of the bootstrap estimates. When you see a distribution that's roughly symmetric, actually the percentile method would have been okay to use in that case. If you see a lot of skewness, that's a surefire sign that, hey, the BCA method is really what you need to be using, because the percentile method might come up with a biased way of coming up with a confidence interval. And I guess the one last caveat is always beware of small samples. The Bootstrap doesn't do great on small samples, but then again, what does? The MLE procedure, the t.test procedure usually aren't that fantastic for small samples either. So yeah, you can almost bootstrap any parameter of the probability distribution you would like. That achieved level of confidence might come in a little bit lower than that target of 95%, but if you're using that BCA method, it's probably going to be fairly close, and you'll be happy with the results at the end of the day. So do we need all this theory? Do we need the central limit theorem? Do we need the asymptotic normality of the sampling distribution of the MLE? Well, yeah, people still expect you to be familiar with these sorts of concepts. And if you could use those confidence intervals that are well bolstered by theory, you should always use those because they're going to be a little bit better than the Bootstrap method. That Bootstrap is here to just fill in the pieces when we don't really know what to do. So Bootstrap, yes, theory, even better.